So let's consider the functions x squared and x plus 1. F of x is x squared, g of x is x plus 1. So I have a graph of those two functions. I'm now going to fill out a chart for both of them. So let's start at, say, -3 and go down to 3. 0, 1, 2, and 3. So if I plug -3 into x squared, what do I get? 9, 4, 1, 0, 1, 4, 9. And you can actually see those points over on the graph. All right, if I plug those numbers into g of x, what do I get? So -3 plus 1 is -2, -1, 0, 1, 2, 3, and 4. Everybody follow me so far? Yeah? Except the ones of you who aren't paying attention? You feeling guilty over there now? No guilt, huh? Okay. Well, let's say I created a new function, and I called it h of x. And that function is created by adding the two previous functions. So f of x plus g of x. But a lot of the times, we actually want to create a function that has a name similar to the way it was created. So if I take function f and I add it to function g, I want it to have a name that's similar to f plus g. So this is going to look a little strange to begin with. I'm actually going to call this function f plus g of x. Now don't get confused. That does not mean f plus g times x. Just like this does not mean h times x. It's the function h written in the variable x. This function's name is f plus g. And because there are two values, we have to put parentheses around it. Because if I just wrote f plus g of x, then you think it's the letter f plus the function g of x. So there are kind of two ways to write this. This is the instruction saying add f and g together. This is the same instruction, but that's usually the way we write it. It's the function f plus g of x. Is that okay? Make no sense? Sadie, you lost? Well, so function notation is something of x. That's function notation. So this is not one function. It's actually two functions. So if we wanted to combine those two functions into one, we could call h of x, which is really common. Or you can actually call it f plus g of x, and that's more common. Okay? All right. Well, what does f plus g of x actually do? Nope, that one. Well, what does f of x mean on the graph? Where does f of x show up on the graph? It's the y values. So this says take the f of x y values and add them to the g of x y values. So I'm going to create a new column, and that column is h of x. And I'm just going to take the y values in the other ones and add them together. So 9 minus 2 is 7. 4 minus 1 is 3. 1, 1, 3, 7, and 13. Everybody follow me? So this function is now f of x plus g of x. So let's graph this function and see what it looks like. So I'm going to be graphing the x column compared with the h of x column. So -3, 7, so 3, 4, 5, 6, 7, and -3. It's right here. -2, 3, so -2, 1, 2, 3. Okay, negative 1, 1. So right here. And then it's hard for me to see. Help me out. 0, 0, 1 is right there. 1, 3. So 1, 3 is right there. 2, 7. So right here. And 3 is going to be way up above. Can anybody make sense of that? What's that? That's a good question. You would think that it would be quite different from what it is. But let's look at, for instance, negative 6. Negative 6 squared is 36. Negative 6 plus 1 is going to be negative 5, and that's going to be 31. So that's a bigger difference. So near the center, it didn't change much, but on the edges, it's going to change a lot. So what's happening here? So let's compare it to, say, the quadratic. Okay? So this point moved down a little bit. This point moved down a little bit. That point didn't move. This point moved up a little bit. This point moved up quite a bit. And this point moved up a lot. Anybody make sense of that? Well, there's a negative x right there that didn't move, but you're on the right track. Okay, let's compare it to the line. Okay, so if we compare it to the line, this point moved up a lot. That one moved up. That one moved up just a little bit. That one didn't move. This one moved up a little bit, and that one moved up quite a bit. Good. Okay, so it probably makes more sense in this case to compare the quadratic to the line instead of the other way around. So let's go back to, I don't think it'll let me. Let's look at the numbers. These numbers here. The value of the quadratic was 9, and the value of the line was negative 2. So if I were to draw the value of the quadratic, I missed, but the value of the quadratic is that, and the value of the line is this, are those two lengths going to work together or against each other? Against each other. How come? One's negative and one's positive. So, in theory, I should be able to take this piece up and set it there, and look. That's where the point went. Could I do it the other way? Could I move the red one? So the red one should reach from the line to the point. Oops. That won't work. There you go. Okay, so let's look at the next set. This distance versus this distance. So it should be able to move that up there. And there you go. Why did the next point not move? And instead of it, say, because the line intersects the x-axis, which means I had a value of 0. So if you look at this particular row, the f of x value was 1, and the g of x value was 0, so the h of x value is also 1. So when either of the two graphs hit the x-axis, then the point on the other graph is not going to be changed. Okay? So here's a distance to the quadratic, and here's a distance to the line. Are those distances going to work together or against each other? They're going to work together because they're both positive. So I can move this green line up, and that matches. The last one, the quadratic and the line are actually about the same length, so, well, not actually true. That should have been a little bit longer. All right, well, if I get rid of all of these lines, is there a way to do the whole thing without having to graph individual points? Is there a way to graph f of x plus g of x? You just use the equations. So f of x plus g of x is going to be x squared plus x plus 1. So x squared plus x plus 1. Does that simplify it all? No. And that will be the graph that matches those blue points we've done. I can show that to you. It's a little bit tricky, but it can be done. So let's change this to x squared plus x plus 1. Go down. And we'll do, oh, I don't need that other one. Okay, let me take a picture of this, and then I can make it see-through. Okay, this is kind of tricky to see, but watch this parabola here. It should perfectly match those blue dots. Okay, I'm not a very good artist, but there we go. So we ended up taking one function and adding another function to it. How would subtraction work? If you had f of x positive and g of x positive and you subtracted them, what's going to happen? It's going to go down. What if you had f of x positive and you subtracted a negative g of x? It's going to go the other direction. So if we compared x plus 1, x squared plus x plus 1, yes? So now I'm going to graph x squared, and I'm going to subtract, and I have to subtract the whole thing, so I'll put it in parentheses, x plus 1. And then let me, if I graph the original, it should be right in the middle of these two. So those should be 3 parabolas right in a row. Can you see that? Ah. So let's take a picture of this. Then I can draw on it. Oh, shoot. Oh, nice. Okay. So if you look at the vertex of this, there's the vertex of the original. Here's the vertex of the plus. And, well, there's the vertex. You can see that those are in a line. And every time you switch the function, it's going to be a little bit different, but it's the idea of if one function is above and the other function is above, they work together if you're adding. If one's above and one's below, they work against. If one's below and the other's below, then they'll go down. So you can squiggle all sorts of things. What's really tricky is when you multiply. Multiply is a big problem because if I did 1 times 0, that's going to turn it into a root, right? If one is already a root, then the other is automatically going to be a root. So if I graphed x squared times x plus 1, watch what happens. So x plus 1, wow, thank you. So x plus 1 times x squared And you could go through and look at the points, but with multiplication, really funny things happen. This is x to the third plus x, you're right. So you see that the left side is below the x-axis? Well, if I look back at my originals, what is it about this that shows me that the multiplication is going to be below the x-axis? It's positive y values times negative y values. And on the right side, you have positive y values times positive y values. But as far as the shape is concerned, there's no easy way to determine what it's going to look like. Adding and subtracting is simple. Multiplying is a problem, and dividing is even worse, because anytime you divide by a variable, you get either a whole or an asymptote. So we're going to spend just a little bit today adding functions together. It's a super simple assignment. A lot of what the book does on this assignment I don't like, so we're not going to do all the problems. So turn to page 139. Let's look at number 4. Well, we'll do number 1. Let's do number 1 together first. One 39. So we have an f of x, we have a g of x. We need to calculate f plus g of x. So x minus 4, or square root of x minus 4 plus 2 minus 3x squared. I just added those together, right? Technically, it's plus negative 3x squared, but I cheated. Can I simplify anything? No? Okay, here's a question. No, you can't, because square roots and square roots and regular numbers they're not like terms, so you can't do anything. So in this case, we have a whole bunch of y values, but the y values in the first function are limited by the x values. Which x's are you not allowed to plug in? Anything below, what did you say? 4. So if we take the inside of the square root, x minus 4 is greater than or equal to 0, and add 4, x has to be greater than 4, or equal to. Because if it's 3, 3 minus 4 is negative, and that creates an undefined function. So this is the new function, and it wants you to state the domain. Well, the domain is every x bigger than or equal to 4. So the domain, the smallest domain of each function is the domain that remains. If one function has a full domain and the other has a partial domain, that partial domain is going to kill the domain in the other one. So let's look at letter B. F minus g. So the square root of x minus 4 plus 2, right, minus negative 3x squared, which ends up being plus 3x squared. What is the domain of that? It's the same. X is greater than or equal to 4. Okay? And you do have to be careful. It's not always f plus g or f times g. If you look at number 2, some of those have g first. So you have to pay attention to what it's saying and follow the order that it gives. If it's addition and multiplication, it doesn't really matter, because addition and multiplication commute, but subtraction and division do not commute. Okay, so letter C, f times g. So I have square root of x minus 4 plus 2 times negative 3x squared. So all I need to do is distribute there, and distribute here. So negative 3x squared square root of x minus 4 minus 6x squared. At the domain, it's still x greater than or equal to 4. No, not necessarily. Well, the domain errors only occur when the denominator is 0 or when you have a negative square root. So we have to look underneath the square roots, and we know that whatever x minus 4 is, it has to be 0 or positive. So you just set what's in there greater than or equal to 0. So x minus 4 is greater than or equal to 0. Add the 4, x is bigger than or equal to 0, or 4. Okay, division looks really awful, but division's usually the easiest to do. Square root of x minus 4 plus 2 over negative 3x squared. Can I simplify that? Nope. So what is the domain? Right, so we have two things going on. X is not allowed to be 0, and x has to be greater than or equal to 4. Go ahead and say it. I don't even need that much information. Does this one already exclude that one? Yes. So we actually didn't need the equals 0, but you're fine if you put it there. What if it would have been x cannot be equal to 5? Then I need it, because 5 is actually in this set, which can happen. Okay, so again, because I think that the book is quite foolish, I want you to do 4, 5, and 6. That's it. So you have 3 problems with 4 parts each, and you have about 17 minutes to do it. Tomorrow I will take a look at finding something different. This book really is kind of junky at the moment. So I'll see what I can do. Good luck.